as we get into our new unit here, we're going to be using the rules that you already know. You're definitely going to have to know those rules a lot as we move forward. But in this unit, we are going to be adding in one more rule. And it's all going to be built off of some stuff we do today. We're not going to get the new rule today, but we're going to be laying a foundation for it today. So, we're starting with this problem, where we're finding the derivative of y equals pi sine of x. Now, first of all, do I need to use product rule here? No. Because pi is a constant. It's not a function. Now, can you use product rule? Yes, technically you can, but when you find the derivative of pi, that'll be 0. And so you don't actually really need to. And so let's not. Let's just go straight to finding our derivative. So that's going to be y prime equals our constant times the derivative of our function. So the derivative of sine is cosine, so it's all just pi times cosine of x. And that's our derivative. That's all you have to do for this one. Okay, no problem. Now let's find the derivative of this one. Right, now the first step is identifying what this really means here. Because notice we got sine squared, right? So this, just as a kind of way to process this through, this is the same as pi. Is the pi being squared here?
No.
No, only the sine is being squared. So this is like pi times sine of x squared. That means the exact same thing. It's just that when we write it in this form, it's considered simpler to just write it like this. So that means the same thing. But because that's what we're really dealing with, then when I go to actually find the derivative of this, really what I'm thinking of finding the derivative of is pi sine of x times sine of x. Because squaring something, of course, means multiplying it by itself. And so this is what we're going to find the derivative of. So please find the derivative now from there if you haven't yet. All right, so now we go and we find our derivative. And for doing so, in this case, do we need product rule? Yes, we do, because these are our two functions. So it's going to be sine of x times sine of x. Now notice then that the pi is still just going to be hanging out up front of the whole deal. So I'm going to do pi, and you can either put the pi in each term individually, or you can do pi and then the parentheses. Either way you want to do it is fine. So I'm going to do the derivative of sine times sine. So that's original sine of x times the derivative of sine, which is cosine of x, plus derivative, the derivative of the first sine is cosine of x, times the original. But of course we can clean this whole thing up a bit, right? And so y prime actually equals, well, the sine x plus the sine cosine plus the sine cosine is 2 times sine of cosine, and multiply that by pi, so we get 2 pi sine x cosine x. Now there's nothing magical about writing the sine then cosine. If you wrote it as 2 pi cosine x times sine of x, it's also fine. But this is then our final answer. And notice that this is not the same as just having taken the derivative of the sine here and like turned it into y prime equals pi cosine squared x. Notice it doesn't actually equal the same thing. So that tells us that we cannot just take the derivative of the sine and call it squared. It doesn't quite work that way. So we end up actually having to use product rule in order to be able to find this sort of derivative. All right. Then next up, now let's find the derivative of this one. And you might be looking for a shortcut, a way to get around doing it, but no, I'm afraid we actually are going to have to multiply this out and turn it into pi times sine of x times sine of x times sine of x. And then we need to be able to find the derivative of that. And you'll notice that as we find the derivative, then yes, we need product rule, but actually there's 3 terms there. So how do we deal with that? Well, pick 2 of them and make them a function, and pick one of them and make that the other function. So for instance, as I look at this, I'm going to do that. That's basically the way I'm seeing it when I do product rule. It's just that when I go and do the derivative of this second function, because that's sine times sine, I'm going to be using product rule within that part of it as well. All right, so we're going to go y prime equals, the pi is just going to hang out front. I'll worry about distributing it in later. That way it's a little less cluttered. So it's going to be original times derivative. So the original, that's the first one, right? So that's just going to be the sine of x as it was. But my sine of x is now going to have to be multiplied by the derivative of sine times sine. So that's going to, I'm just going to go ahead and do that in red so we can see where that's coming from. Now I do the derivative of sine times sine, which actually we already know from the last problem. If you remember what the derivative of sine times sine is from the last problem, you can use it. But if you don't, we can do it out the long way. Original times derivative plus derivative times original. And so that is original times derivative in product rule. So now I'm going to have to do plus derivative times original. So that's the derivative of sine. So that's going to be the cosine times the original. So that's then times the sine times the sine. So then sine of x, sine of x. Try that again. There we go. All right. Well, we found the derivative, but yes, I do want it cleaned up. So, clean this up, please. Combine your like terms, all that kind of good stuff. All right, and so when we go and clean this up, the pi, of course, is still just hanging out front. But then as I look on the inside, when I multiply this sine into these parentheses, notice both of those inside become sine squared times cosine. But this last one also becomes sine squared times cosine. So really, inside of my parentheses here after my pi, I have 3 sine squareds times cosine. Well, of course, then that would mean that y prime would equal 3 pi sine squared cosine. That would be our fully simplified form at that point. Now, I did this out the long way where I just found that derivative, but I did say that we could have used the derivative that we found the last one. In the last one, we found that that derivative was 2 sine cosine. And so you could have then been multiplying sine times 2 sine cosine, so that would have given you 2 sine squared cosine, and then plus another sine squared cosine from that. So that would still give us our 3 pi sine squared cosine. Now keep this work handy because after we do a few more of these, you might start noticing a pattern on how we can get to this sort of a solution a little bit faster. But that's going to require, in order to create a pattern and find a pattern, trying a number of different ones. So we're now going to take a look at some square root functions. So please find the derivative of this function. Now, right now, we got this 25x inside the square root. We don't really have a way to find the derivative with that 25 still inside of the square root. So the very first thing you should do is rewrite this function. Now, when you see the square root of 25x, that means you can do the square root of the 25 and then the square root of x. The square root of 25, of course, is 5, so this whole thing just equals 5 times the square root of x. Now we can find our derivative, and it's actually much easier now to find the derivative as well. So f prime of x then is going to equal 5 times, now the derivative of root x, remember that becomes x to the 1/2 power, and then I do minus 1 from the 1/2, and then I multiply the 1/2 out front using power rule, and so then this becomes 1/2 times 1 over root x. Of course, you probably didn't show it that way. You probably went straight to the final step, which would have been 5 over 2 root x. And that would be it. That would be done. So now, having done that last one, you now can actually find this derivative, although it might feel a little bit like you can't, but you can using the exact same method. And so the first thing that we did last time is that we rewrote it, right? Because with that 3x on the inside of the square root, we don't have a technique for dealing with that 3 on the inside other than simplifying. So if we do that, then the first thing I'd have to do is do the square root of 3. And I don't really want to mess around with the decimal. So what do? Well, I can just write it as root 3 times root x, because root 3 is still a constant. And so we then could go ahead and do the same thing that we did last time from here. And so it's going to be the derivative of the root x, so that gives me 1 over 2 root x. And then this is being multiplied now by the root 3, which means that I can then just simplify it a little bit here and put that root 3 on the top. So it becomes root 3 over 2 root x. And so just like that 5 ended up hanging out on top in my final answer in the last one, my root 3 just ends up hanging out on top in this final answer as well. And I can do that because remember, root 3 is also a constant. So then, let's continue playing with our square root functions here. Please find this derivative now. And the first thing you're probably going to be inclined to do is pull out that root 3, which is a great way to start. But notice I still have the square root of x cubed. Well, again, we still kind of have this function of x cubed within the square root function. And so before you go too much further, you definitely do have to, in this sort of a case especially, make that into something that we can deal with. And the nice thing is that with square roots, rationals like this, or radicals like this, we can go ahead and turn it into a rational exponent. And so really you're going to be finding the derivative of x to the 3/2. All right, and so I use power rule, same as always, and then we clean up. So that's going to give me f prime of x equals, on the top, I'm going to have 3 root 3, and on the bottom, just the 2 on the bottom, because my x is also inside the square root. Now, I can write it like that, but we don't actually have to write it then as root 3 times root x. Because we now have those square roots times each other, we can just write it as square root of 3x to clean it up just that extra little bit. Right now with this one, there is a potential pitfall with this one because you may well be inclined to start by writing this as root 3 times x to the 3/2. But that's not quite right, because the parentheses change things up on us a little bit here. Because you'll notice that the 3 and the x are being cubed here. And so really the first thing I'd want to do is do that cubing. And so what is 3 cubed? 27. So it'd be 27 x cubed. And we now could start progressing from there. And so f of x is going to equal square root of 27 times the square root of x cubed. But even that can be cleaned up a little bit more. And so, first of all, square root of 27. We can simplify that radical a little bit. Notice that 27 is just 9 times 3. The square root of 9 is 3, and that other 3 is still left behind. So yes, that is 3 root 3. And of course, to deal with the square root of x cubed, I'm going to be turning that into x to the 3/2. But now it should feel very similar to the last one that we did, right? So here, to find our derivative, f prime of x now, we end up doing the, I'm going to write out the long way first, 3 root 3 times 3/2 x to the 1/2. Positive 1/2, so that's going to stay on the top of our fraction then. So then f prime of x equals 9 root 3 x over 2. You might have noticed that everything that we've been doing so far has basically been a composition of functions, where we've had some function inside of another function, like sine squared is really like composing sine with x squared. Well, here we're going to actually formally bring out the composition aspect of that. So here we're going to find our derivative of h of x. H of x is a composition. So please write down the problem, do the composition, and then find the derivative. All right, so first thing we want to do is we take whatever g of x equals and we plug that in for x in the other equation. And so that's what we have so far over here. And now I just want to clean it up before I worry about finding the derivative. Nothing too fancy to do here. I'm going to do the 7 plus the 13, which will give me 20, and then that's just minus 5x. Now I can go ahead and find my derivative, right? So h prime of x is going to equal, what's the derivative of 20? 0. Just goes away. What's the derivative of negative 5x? Negative 5. And we're done. All there is to that problem. So the first thing is just plugging in our composition and figuring out what h of x would actually equal. And did we actually have to go here, though? Could I have found the derivative just from that line right there? Well, up to this point, with everything that we know so far, only if I tried to use chain rule. And I could actually try to do it that way. Like I could do 7 minus 5x times 7 minus 5x. I'm sorry. And use product rule on that. Got to use the right word there. I think I said something different. And so you could have used product rule from that phase if you wanted to, or you could have multiplied it all out. I chose to multiply it all out. All right. So now that we are here, though, we can go ahead and find our derivative, and whichever way you approach it, your simplified derivative will be the same thing. So the derivative of 62, of course, is 0. The derivative of negative 70x is negative 70. And then the derivative of 25x squared is 50x. And so that would be your final answer. Now, if you chose to do it by multiplying it all out, this is how we get there. But it's a big pain to have to multiply it all out, right? Some of you might have seen that and decided, well, instead of multiplying it all out, I'm just going to go ahead and use product rule with that one like we did earlier. And that would also be fine. So, either way, though, you should end up with the same answer once everything has been simplified and all that stuff. So we should end up here. Some big numbers. Now, could you have gotten the same thing by just doing like a product rule kind of thing? Yeah, you could. Because we could do the 7 minus 5x times 7 minus 5x times 7 minus 5x. And then done product rule kind of like we did before when we were looking at the sign. But it'd be a bit of a pain to have to do that individually for all these different types of functions. It really would be nice if we had some general rules for some of these, right? Like, let's just actually take a look at one of those now. What if I just give you the derivative of g of x squared? Then I could just take any function that g of x is and I could just plug it in, right? So let's find the derivative then of this function. And so to generalize it, remember I can turn that g of x squared into g of x times g of x. And now that I'm there, I can use product rule. And so we use our product rule there. And we end up with something that looks like it should be able to simplify a bit, right? Because notice g of x times g prime of x and g prime of x times g of x, they actually are the same thing. They're just written in a different order, but it's multiplication, so the order doesn't matter. So we actually have two of those g of x, g prime of x functions. And so then that is a simplified version. If we had done this in the first place, we wouldn't even have had to do some of that other work, because I could have just seen, well, anytime I'm squaring a function, I'm going to end up getting 2 times the function times its derivative. Well, that would also be useful if we had done that for the cubic function, right? So now let's go ahead and cube g of x and see what the derivative of that one would look like. And the first thing we do is we see that g of x cubed is the same as g of x times g of x times g of x. Now we can go ahead and start employing the product rule. Now I'm using product rule here. I now need to find the derivative of the g of x times g of x. I don't really have to go through the long way of doing that though, do I? Because remember what I just did. G of x times g of x is g squared of x, or this g of x squared, right? That's the last problem that we did. So I already know that the derivative of that is going to be 2 g of x g prime of x. So I just got that from the last problem that we did. Made my life a little bit easier. All right, so that's original times derivative plus derivative, so that's just going to be g prime of x times the original. So that's just g of x times g of x, or if you chose to write that as g of x squared, that's fine. And now we look to see what we can combine, how we can simplify this whole deal here. So f prime of x is going to equal, well, this first term is going to be 2, let's see, I got 2g of x's here. So I'm going to go ahead and make that 2g of x squared times g prime of x. And then, wait, nope, don't need a parenthesis there. And then the second one, I also have g of x times g of x, so I'm going to go ahead and call that also g of x squared times g prime of x. So just combining the ones that we can, multiplying the g of x's by each other. But now notice that both of these terms are like terms, because both of them are g of x squared times g prime of x. And so we can go ahead and combine them from there. And so we end up with the final simpler form of getting 3 times g of x squared times g prime of x. Which should feel a little bit familiar, because this looks a lot like the answer that we got back when we did that problem with sine of x in it, right? Where we ended up with 3 times the sine of x squared times cosine. And notice that's the same thing this gives us. So any time in the future that I ever gave you some function cubed, you could actually go back to this problem and you could skip over a lot of the work to be able to get there, right? That's what we want. We want to be able to simplify our life a little bit here.